Hey team, welcome to part two of our binary search saga. All right, so let's talk about what is binary search. I think you can guess that binary search is more efficient than linear search, but how exactly does that work? Let's talk about it. So, the basic idea of binary search is how you look up a name in a sorted space, like a phone book, or if you look up a word in a dictionary. Now, when I first started teaching, this was an adequate description of looking up a word in a dictionary. But as new generations of students come in, I have found that you might have used a dictionary like that one time in fourth grade. So if you haven't used a dictionary, you can think about it like trying to find a name in your phone contact list, for example. Like you're not sure where it is, so you go somewhere in the middle and then you go somewhere um, like you're looking a little bit left because it comes earlier, or maybe you're looking right because it comes later. That would be a good example. Or maybe if you are alphabetizing some papers, you know that you can look for a specific thing by, starting in the middle and then, okay, it's not there. Now I'm going to go to one side or to the other side. That's the idea of binary search. If you have sorted information, then you can find what you're looking for pretty efficiently. So here's how it works. So the basic idea is you look somewhere in the middle. This is just the where am I check. So what does the middle look like? How far do I need to go in one direction or another to find what I'm looking for? So when you do that where am I check in the middle of the space that you're searching through, you can compare what is there, what you see in the middle, that middle element, and you compare it with what you're looking for. You decide, okay, first, is this the one that I'm looking for? That would be really lucky. If it's not, you can decide, is my element less than this element? Should I look at the left half or is it greater than this element? So then I should look on the right half. And what is really cool about that is that that means you're eliminating half of the elements. You don't even need to look at them, which is really, really convenient. And then you just repeat this until you find the correct place. So you look somewhere in the middle, you don't find it, but you do see you need to look at one half. And then you look at that half and you go somewhere in the middle of that half. And within that half, you do the same thing. You ask, where am I? How does my element compare with this one here in the middle? Do I need to move left? Do I need to move right? And then you eliminate half of the half, and then you eliminate half of the half of the half. And you just continue eliminating elements until you find the correct place. This is the binary search algorithm. Now, I just gave a very wordy description, so let's look at an example. In the binary search algorithm, you can see this is the array that we're going to be working with. All of the elements are sorted. So we go here from 6, numbers get big pretty fast, and then they sort of even out toward the end. But they are sorted, and that's the important part. So, okay, that is the data that's coming in. Now, the algorithm part, I guess the other data that's coming in is the value that you're looking for. So keep that in mind. The two things that a binary search requires is the haystack, which is all of the elements in the array. So the array is the haystack, and the needle is the thing that you are looking for in that haystack. Okay, so let's talk about the algorithm. If we have those inputs, what can we do to try to find the element that we're looking for? So when we're working on the algorithm, we need to keep track of a couple of different variables. So we need to keep track of the lowest item under consideration right now. We need to keep track of the highest element or the index of the highest element that is under consideration right now. And we also need to keep track of that midpoint element, where are you or you are here element. So next, the thing that we need to keep in mind is that we're going to stop searching if the element at mid, the you are here element, if that element is the one that we're looking for. So that's the first option. But if our low equals our mid equals our high, that means that this is our last chance. The thing that we're looking for, our needle is either right here or it's not in the list at all. So those are the reasons that we would stop searching. Okay, so our goal is to just constantly reassign these three variables to represent smaller and smaller ranges. Remember, we were cutting it in half every time because our element was either going to be on the left side of the half or on the right side of the half. And then we are going to either find the element or we're going to find where that element should be, but it is not. So let's go through more descriptive of an example here. Okay, so we have this search, binary search. We're looking for the item 33, and we as humans can just look at it and say, oh yeah, it's in index 4. But the computer in a linear search would have to look through every single item until we found number 33. Or in linear search, we are going to hop around a little bit more. So let's say we have binary search 33. So we're searching for the value 33. That's our needle. And array is our haystack. So when we enter the algorithm, we set our low to be the first index in the array, which is index 0. We set our high to be the last index of the array, which is length of the array minus 1. And then we select our midpoint. We're going to do this pretty simply. We're just going to add low to high and then divide by 2 with integer division. So with that, that means 0 plus 14, we get 7, which is our midpoint. We're going to call that mid. So now we've set the three variables that we need to consider. Now we compare our element, our needle, to the one that's being considered right now at mid. The one we're considering right now is item or at index number 7, and it has the value of 53. Since 33 is less than 53, we can ignore all of the elements to the right of and including 53. We know it's not 53, so we can exclude it and all of the elements that are bigger than it. And that means we set our new high to our previous mid minus 1. So our previous mid, let me go back. Our previous mid was at index 7. And what we're doing is we are moving our high to now represent the first value to the left of our previous mid. So we move our high, and then we need to find our mid again. So we're going to add 0 plus 6 is 6 divided by 2 is 3. So here we are selecting item at the item at index 3, which is the value 25. So the value 25 is our you are here point. We are looking, is this value less than 25? Is it greater than 25? Is it equal to 25? And since we're looking for 33, we know that our value is greater than 25. So we can ignore 25 all the way down to the beginning of the array. We know it is not 25 and it is greater than 25. So all of these elements are irrelevant. and we can ignore them again. So with this, take a second and think about it. What will be the next values of low, mid, and high? Take a break. Did you pause the video and decide? I hope you did. Okay, let's talk about it. We'll go from the start. So here, we have 0, 1, and 2. So that would be we move low, low stays at 0, high moves to 2, and mid becomes 1. Okay, that would mean that we would be looking for 33 only among values that are less than 25. And that doesn't seem right because we're looking for something that is greater than 25. So we need to be looking over here. So starting at 0 is not looking good for us. Let's not include that. Now, if we look at B, 1, 2, and 3, that means we're still looking at values that are less than 25. And we are considering 25 itself, which we know is not the item that we're looking for. So we shouldn't keep it under consideration. C is 2, 3, and 4, still involving two values that we know are not 33. D is, gave away the answer. So D is 3, 4, and 5, which means that we're never going to be able to look at 6. What if our element was in 6? And also, we've already searched 3, and it's not 3, so we don't want to keep considering it, which leaves us with E. Low, mid, and high are 4, 5, and 6. High stays exactly where it is. Low moves to the value just after mid, and the midpoint is going to be calculated to be the midpoint between those two indices. So we're going to end up with this. We have low at 4 and high at 6, and our mid is somewhere in between. Now we're looking at this value of 43. This is our you are here point. At 43, as our mid, we're going to compare 43 to 33. We know they are not equal, and 33 is less than, which means it's going to be to the left of. So if it is to the left of this, that means that we now need to move to the left. So it is not at index 5. We need to move high to 1 to the left of 5, which is 4. Low stays the same. So both high and low are now at index 4. So we have low equals high, and we calculate the mid. Low equals high equals mid. So we know whether we find it here or not. This is where our algorithm is going to stop because there's nowhere else to look. So we compare, is the item at index 4, is that our needle? And we can say, yes, thankfully it is, because it was sort of our last chance. And luckily, we found it there. So our algorithm, it's not going to return 33 because 33 is the thing we were looking for. What it's going to return is the index of 33 in the list. So the item that we return from this algorithm is the index, the number 4. Okay, so that is how binary search works. If you remember, we started with a whole array. We looked at the middle element. We decided, is it greater than or less than my item? We decided that the thing we were looking for was less than. And so then we took the middle of that space, just that half, and then compared again. And then we looked at the appropriate half again, and we are just continually cutting in half until we found the thing that we were looking for. So given an array with 1 million elements, okay, so this is the same problem that we were looking at before, except now our array is in sorted order. It used to be in random order when I asked this question in the first section, but it is in sorted order now. How many elements do you expect to look at in the worst case when searching. So before we were looking at the average case, now we are looking at the worst case. In the worst possible case, what would it take? Take a second and think about it. I hope you paused the video, but let's talk about it. Okay, so let's look at A. If the item was present, we only had to look at one item. Gosh, that would be cool, wouldn't it? So we just know exactly how to get there and we look at exactly the one that we're trying to find. But unfortunately, a binary search isn't quite that efficient. We can't just find it right off the bat. So I don't know about that one. So then there's B, which is about 100. That sounds reasonable, but it seems a little bit high. Then we look at item C, which is about 20. And you know, that sounds right because we are always cutting in half and in half and in half and in half, which says log to me. So if we're trying to take a log base 2 of 1 million, it's going to be about 20. I think it's a little over 19. So about 20 makes sense. So let's look at the second column. If the item is not present, we would have to look through all 1 million elements. Now that doesn't make sense either, right? Because if what we are searching for doesn't exist in the array, that is when low equals mid equals high. And the worst case for that is still going to be less than 1 million. So C is not quite right. Let's look at D. We've got 100,000. That is way more than what we need to look for in uh, what in our array using binary search. We said that it was probably going to be about 20. So if the item is present, we've got 20, and that's if the item is present. If the item is not present, it's still about 20, right? We're either going to find it or we're not going to find it, or going to find exactly where it should have been in about 20 steps. So with linear search, we had to, I guess I should make clear, E is the correct answer here. With linear search, when we talked about that, if the item was not present, we had to go through all 1 million items. And if the item is present, we would have to go through about half. But here, we are able to cut both of those numbers, even in the worst case, down to 20 instead of 1 million. That is pretty cool. So let's talk about binary search. So the number of items that are visited in a binary search, it's approximately log base 2 of n. So if you have n elements and then you cut it in half and then you eliminate half of them, and then you have this remaining smaller spot and you cut that in half again and you eliminate the remaining, that's what a log does. It just divides in half. Log base 2 is going to divide in half so many times, starting at size n. So that's how you can determine how many items are actually looked at or visited in this binary search. So it's approximately log base 2 of n, which is really cool. There are a couple of things you need to keep in mind with this. So in a binary search, if all elements are unique, then the results are always going to be the same. But if you have duplicate elements in your array, there's a slight difference in how linear search and binary search are going to behave. A linear search is always going to provide the very first element of, or that is equal to the needle that you're looking for. It will be the first one in the array. A binary search doesn't guarantee that because it could find one of the middle elements of the duplicated. So let's say there were 3 33s. A binary search might find any one of those three. It's just whichever one it finds first. So a binary search it does guarantee correctness. It will return to you a or an index of the the needle that you're looking for, but it doesn't necessarily return the first index. If you're trying to find the very first index, you might have to take the result of the binary search that you performed and then just move left until you identify which one is the first. But that's a variation that isn't always necessary. But if it is necessary for you to identify the first one, then that is a modification you have to make to the algorithm. Okay, so Java, which is the language that we are working in, Java does have a binary search built in. So if you're trying to search an array, you can use arrays dot binary search. What this is going to do is it's going to return the index if that element exists, or if it does not exist, it is going to return the index where the element should exist. So let's say we had low equals mid equals high, and that was in our example, it was at index 4, right? Well, let's say that the element we were looking for, it wasn't number 33, it was 34 right there. So our needle was not in the array at all. If that's the case, what we would return is this insertion point, which was our value 4, that was the last value of low equals mid equals high. And we negate it. So this now becomes -4 minus 1 equals -5. I want you to take a second to think about why we would have to do this -1. Think about it. We have to do -1 because of our zero indexing. So 0 is an acceptable index. If we were to negate 0 here and just do a negation. So if it was in number 4, it should have been in index 4. We can say, oh, it should be a -4. But what if it was supposed to be inserted at position 0? We can't say it's at -0 because Java doesn't allow positive and negative versions of 0. So what we do instead is we subtract 1 to make sure that if it's supposed to be at index 0, then we say that it would be -1. And if it was supposed to be at index 1, we're going to say it would be at -2. So this way we can figure out, where it was supposed to be inserted in case it wasn't there. And this can be really helpful when you are you're like, okay, does it exist in the array already? And if not, I'm going to insert it. This would be a good example of why you would want to know where it should be inserted. So you don't need to do that search again when you're trying to insert an element. Okay, this has been hinted at a couple of times because my mouse is a little overeager to change things. But this is the end of part 2. In part 3, we're going to actually get our hands dirty with some code. See you then.